No questions? Things are all right? How's the weekend? Yeah, is it ever? All right. So last time we chatted about solving systems of linear equations through elimination. And basically try to get this down to what we refer to as a triangular system. We're going to, in the next section, we're going to talk about how to just keep track of the coefficients. And basically that's all we're trying to do, right? When we're trying to put this in a triangular system. Remember, our goal to put it in a triangular system is to have a coefficient of 1 on the x up in the upper left-hand corner, get rid of the x's in the other two equations, then have a y by itself in that second equation, try to get rid of the y in the third equation, and then you have just an equation with z at the bottom, get a value for the z, and you can work your way back up. So that's our process for doing this. All right, so notice that we already have a single x up here in our first equation. So we need to worry about that. So let's work off of this single x and get rid of the x's in the other two equations. So if I work with the x plus y minus 2z and the x minus y plus 3z, I guess I need to put the constants on the other side there. What do you want to do to get rid of the x? What should we do? The reason why we want to work off of this x here to get rid of this one is what can I do to this x so that when I add down, we get rid of that one? You know, multiply by -1, right? So our notation for that, and we'll flip the notation slightly when we just start keeping track of coefficients, is we'll do -1 times the first equation, add it to the second equation, and replace the second equation. Now again, we're doing this all in one step, so we're really not changing the first equation at all. Gives us a 2z. We're only changing the second equation as we go along here. So if I do -1 times the x and add to the x, we'll get a 0, right? If we do -1 times the y and add to -y, what do we end up with? -2y. -1 times the 2z gives me positive 2z, plus the 3z gives us 5z. And then -1 times -1 is +1, plus the 7 gives us 8. So again, I'm just running the negative, I'm doing it all in one step, not changing the first equation. But I am doing -1 times each of those and adding it to each of those for the next equation. Does that make sense? Okay. Now to save some writing, I'm going to go ahead and put this third equation in the same spot. And now again, I want to work off of the first equation and get rid of this 2x. This is what that elimination process is. So what do I need to multiply the x by so that when I add down, I get rid of the 2x? -2. Good. That's why we always want a 1 up in that upper left-hand corner. It makes our numbers work out nicer, right? I don't have to guess at what we should multiply by. All right. So we'll do -2 times equation 1 added to equation 2. Or sorry, equation 3, and replace equation 3. So again, -2 times the x added to 2x will give us 0. -2 times y is -2y minus 2y gives us -4y. Negative 2 times the negative 2z gives us positive 4z plus 6z. That gives us 10z. Negative 2 times negative 1 is positive 2 plus 14 gives us 16. Everybody following where I'm getting those numbers from? That's the important part here. Because this is what we're going to be doing a lot the rest of today and all of Wednesday. Okay? It's the exact same process. By the way, was there anything important about necessarily the x's or the y's or the z's, or was the important part the coefficients? The numbers, right? The coefficients, right? We're not doing anything with the x's except we're not doing anything with the x's, the y's, and the z's except combining like terms, right? That's all we're really doing. So that's what we're going to head towards in the next section later on today. Is really we just need to keep track of the coefficients as we go along. All right. So far so good. So again, remember our goal here is to put this in a triangular system, and then we can back substitute, right? If we get it done triangular, we can figure out what that z is, work backwards in the next equation, figure out what y is, work backwards in the first equation, and figure out what x is, right? That's that back substitution process. All right. So in this process, notice that we got a 1x up in the upper left-hand corner and got zeros below it. I would now want to work on this one and get a 1y. That's the process. If I want to get a 1y, we will just take negative 1/2 of equation 2 and replace equation 2. The reason why we want to get a 1 on these coefficients in the next step is because it makes it easier to figure out what we need to multiply that equation by to get rid of the thing that's below it, right? When we have a 1x up here, we know we need to multiply it by a negative 1 to get rid of that one, and multiply by a negative 2 to get rid of that one. This is the opposite of the coefficients, right? So when we divide everything by negative 2, we don't change the first equation at all. The second equation becomes y minus 5/2 z equals negative 4. And we don't change the last equation. Again, just to emphasize, the reason why we get a 1 for the coefficient on the y is because it's a lot easier to figure out what we need to multiply that 1y by to get rid of the y below it. So that's why we're going to get a 1 there. And this is exactly the process we're going to use when we switch over from keeping track of all the equations to just keeping track of the numbers. All right, so now let's look at this equation. Again, our goal is to put it in that triangle form, right? See that nice diagonal going down so that we get rid of this y here, and then we can solve directly for z. That's our goal, right? Okay. So now, now what do we need to multiply this y by to make this negative 4y go away? What do we add down? What do we need to multiply this by? Positive 4, right? So the next step will be take 4 times equation 2, add to equation 3, and replace equation 3. So that doesn't change the first two equations, right? We're doing this multiply and add as one step, but we're not really changing that second equation by doing the multiplication. All right, so 4, now look at these equations. 4 times y added to negative 4y gives me 0. What do you get when you multiply the 4 times 5/2? What do you get? Yeah, get negative 10, right? There's the minus sign there. Negative 10z plus 10z gives us 0, right? So I actually get a 0 on the left-hand side. What happens in the next one? When you do 4 times negative 4, gives you negative 16. And add down, what do you get? 0 as well, right? So notice that last equation says 0 equals 0. Is that a true statement or a false statement? True, okay? So this, remember when we had this in those 2x2 systems, those 2 equations and 2 unknowns, this is when we got infinitely many solutions, okay? So this tells us that we have a dependent system. Still consistent. Remember, consistent means at least one solution. But when it's dependent, we get infinitely many solutions, all right? So now that we've got this written in this form, let's figure out how we write our solutions. So in these 2 equations, that's all we have left, right? This isn't giving me any new information. Okay. So what we'll do is we will solve this one for y in terms of z, plug that into the first equation, and solve that for x. Okay? So our y will be 5/2 z minus 4. Just adding your 5/2 z over. We now take that and plug it into the first equation and solve for x. So I took out, notice that the first equation was x plus y minus 2z. Took out the y, plugged in the 5/2 z, and now simplify. 5/2 minus 2 is 1/2, right? And I'm going to subtract it to the other side. So we'll have x equals negative 1/2 z. Add your 4 over and get a plus 3. And then if I want to write this in that set builder notation we talked about last time, since it's a dependent system, what that means, besides the fact that we get infinitely many solutions, it means that one or more of the variables depend on a choice of another variable. That's what dependent means. Okay? So the way we've got this is we've solved for y and we solved for x in terms of z. So that means that x and y depend on z. That's the dependent part. Okay? So z being whatever we want, the y has to be the 5/2 z minus 4. The x has to be the negative 1/2 z plus 3. We get to pick whatever we want for the z, right? So that's when we write that set builder notation. That z can be any real number. And that's telling us that we have infinitely many solutions. So again, we pick what we want for z, and then we know what x and y are. That's what that dependent part means, right? The x and the y depend on the z. Versus when you get exactly one solution, you have x equals a number, y equals a number, z equals a number. That makes sense? So notice that when you get this 0 equals 0 at some stage, that's a true statement. That tells you they have infinitely many solutions. If we would have had 0 equals something other than 0, what would you have said? No solution, right? That's an inconsistent system, right? So if you get to a point where it says 0 equals 2, for example, you quit. There's no solution and you're done. Questions on that one before we do the next one? I'm being very purposeful about going all through these because hopefully it'll make more sense when we switch it over and just keep track of the coefficients. All right. So let's look at this one, asking us again to solve through elimination. We've got 3x minus 2y plus 2z equals negative 2. X minus 3y plus z equals negative 2. 2x minus y plus 4z equals 7. Remember, the process is very repetitive. Single x up in the left-hand corner, get zeros below it. Single y in that middle position, 0 below it, and then try to get a single z at the end, right? That's the goal. Right? Okay. Now remember, we can always do one of those three elementary operations, right? You can multiply by a non-zero constant, you can swap equations, or you can do the funky one that we've been doing in the last few examples, right? Multiply by a constant, add to a second equation, and replace the second equation. To get a 1 in this particular example, to get a 1 in the upper left hand, a 1x in the upper left hand corner, what's the easiest thing to do? Do you see a 1x in a different equation? Yeah, just swap them. Yeah, just swap the first and the second equations, right? I can move equation 2 up to equation 1. All right, so this is the original system that I'm writing down. My notation for swapping is a double-headed arrow. Other notations might be like a little tilde. But my notation for swapping is I'll use a double-headed arrow. Basically it just says I'm flipping equation 1 and equation 2. So literally just flip-flopping the positions. So far, so good? All right. So now we want to work off of this x to get rid of the x's in the other two equations. That's why we refer to this as elimination, right? Right, I'll eliminate the x's. So what do we need to multiply? And anytime you're doing elimination, whether we're doing this with variables or doing it in the system, what we're going to talk about later today, we're always going to work off of this to eliminate the other two. Okay? We're going to eliminate this, we're going to eliminate these two by working off of this one. So what do we need to multiply the first equation by to get rid of the 3x in the second equation? Negative 3. So we'll do negative 3 equation 1 plus equation 2, replace equation 2. Now before we actually do that, let me go ahead and write down the other one as well. What do you need to multiply equation 1 by to get rid of the 2x in the equation 3? Negative 2. Good. Again, neither of these operations change equation 1. Even though we're multiplying equation 1 by a constant, we're doing that as a kind of a middle step, right? The whole goal of this is to get rid of the x's in the other two equations. So we're not really changing the first equation. We're just doing it as a computational step in the middle. All right, so let's go through the steps. Negative 3 times x is negative 3x, plus 3x gives me 0. Negative 3 times 3y gives me 9y, plus negative 2y gives me a positive 7y. Negative 3 times z is negative 3z, plus 2z gives us a negative z. Negative 3 times negative 2 is positive 6, minus 2 will give us a positive 4. Is that okay? Is that okay so far? I know, it's a lot of computation, isn't it? Yeah. It's a lot, I know. Let's do the next one. Negative 2 times the x is negative 2x plus the 2x is 0. We're rigging it so that makes the x go away, right? Negative 2 times negative 3 is 6 minus 1. It should be 5y. Negative 2 times z. Negative 2z. Plus 4z. Positive 2z. Ooh, this is not going to be a very good example because this is going to be ugly fractions. That's all right. Negative 2 times negative 2 is 4. Plus the 7 gives us 11. So far, so good? All right. So that's step one. Like I said, this next one's going to be kind of ugly because we're going to get some fractions in here. That's okay. It happens. 1 here, 0 is below it. The next step is a 1 here, right? The easiest way to get a 1 here is to divide everything by 7, right? So I'll do not negative. We'll do 1/7 equation 2 and replace equation 2. So that'll change it to a y minus 1/7 z equals 4/7, and doesn't change the last equation. It's a very algorithmic process. Get a 1, get a 0 below it. Get a 1, get 0 below it, get a 1. And you can keep doing this for larger systems if you want to, but this gets the point across what we're doing. All right, so we got a 1, then got zeros, we got a 1. The next step is to get a 0, right? So what do we need to do to get rid of that 5y in that bottom equation? Good. And do negative 5 equation 2 added to equation 3. Replace equation 3. Again, that does not, pardon me, that does not change either of the first two equations. It does change the last equation. We've rigged it so the y goes away. Negative 5 times negative 1/7 is positive 5/7. 2z, 2 is the same thing as 14/7, so we should get 19/7 z. It's a pretty number. Negative 20 over 7. Yeah, sorry. This part, yeah, I'd like you to write that in there because that tells me what the operation that you're doing. I just think it's easier to follow along. And if you go through the ebook, they do the same thing. It's the same notation that they use. Negative 5 times the 4/7 is negative 20 over 7. That's 11 is 77 over 7. So we get 57 over 7. If I did my math right. Yeah, it's math class. I hope I did the math right. So far, so good? Okay. Then again, what we're trying to do is get this down to a triangular system. Triangular system means we have coefficients of 1 all the way down that diagonal, right? If I want to turn this into a 1, what do I need to do? What do I need to multiply that equation by to turn the 19/7 into a 1? Yep, 7/19. It's good. Multiply by the reciprocal, right? Again, doesn't affect the first equation. Doesn't affect the second equation. Third equation now becomes z equals. Well, notice if you multiply by 7/19, the 7s will cancel. And 57 divided by 19 can be 3. If I did my arithmetic correctly. That's nice. Came out to be a nice number at the end. Yeah. Okay. This puts the system into triangular form, right? For this is a triangular system, right? Pardon me. Now that we've got it in a triangular system, we can do that back substitution process. I have the number for z. I can take it, plug it up here, get y. Take those two values, plug it up here, and get x. By the way, now that we've got z equals a number, how many solutions are we going to get for this system? Just one, right? It's not dependent, right? We've got z equals number, and we didn't get an inconsistent thing, right? We didn't get a false statement. So there's going to be exactly one solution. So now when we plug back in for the y, oops. Plug 3 in for z. Well, 1/7 times 3 is 3/7. You add it to the other side, you'll get 7/7, or 1 for the y. And then finally, we can figure out what the x is. Notice when you put in 1 for y and 3 for z, the middle, those things cancel each other out. We just get x equals -2. So finally then, our solution will be -1, 2, 3 for those. Pardon me. What question do you have on those? No one okay? Again, very, very algorithmic process, right? 1 in the upper left-hand corner, 0's below it. 1 in that middle spot, 0 below it. We'll finally get a 1 in that lower right spot, hopefully. And then work your way back up with them. All right, I'll leave the next two for you for practice. I'll post solutions to them so you can see them. What I want to do is one of the word problems before we go on to the next one. Make sure that we can set up a word problem here. So they give you 3 orders of pizza and salads and sodas and the total price for each of those. And it wants to know what are the prices for pizza, salad, and soda. So again, we've got 3 different quantities that we want to find, right? We want to find the price of pizza, pardon me, price of a salad, price of a soda. So we have 3 things to solve for. So might as well call those X, Y, and Z. So I'll do the X is the price of the pizza, the Y is the price of the salad, Z is the price of the soda. We have 3 variables that we want to solve for. So how many equations do you think we need to set up? 3, right? If we're going to find a price for pizza, a price for salad, and a price for soda, we better set up 3 equations. Is there enough information in the problem to set up 3 equations? Yeah. What's the first one going to be? Good. So 5x plus 2y plus 2z equals 975 is 1. How about another one? Okay. And the last set will be? Good. This okay? Does it work? Okay. So again, remember that our first step, if we're going to solve this system, is to get a 1 in the upper left-hand corner, right? Now, an easy way to get a 1 in the upper left-hand corner is to multiply the first equation by 1/5, right? So I would, especially since you have your calculators and can do things with fractions, I would probably just do that. You can be a little bit fancier and combine some, whoops, not equation 2, equation 1. You can combine some things to get a 1. For example, I could work with these two numbers and get a 1 pretty easily, right? I could multiply this by -1 and add down and get -1. I could also multiply this one by 3 and add up and get a 1. You can do that too. That's pretty fancy. I don't typically do that. I'd rather just do it more straightforward. The more straightforward with this is to divide everything by 5. I know it introduces fractions, but it's a little bit more straightforward. You don't have to worry about trying to be fancy. All right, so multiply everything by, why did I say 2/5? Just 1/5. I don't know where I got a 2 from. Sorry. X plus 2, I know where I got the 2/5 from. I was thinking about the coefficients coming up in here. Divide everything by 5, right? You get x plus 2/5 y plus 2/5 z equals, what do we get when we divide that by 5? 195. Okay. That doesn't affect the other two equations. Probably should have left a little bit more room, but that's okay. All right. Our next step is to get zeros here and here, right? Once you get a 1 in the upper left-hand corner, your next step is to get zeros below it. Okay? What do I need to multiply equation 1 by to get a 0 in equation 2 there? -3. So one of the operations we'll be doing is -3 equation 1 plus equation 2, replace equation 2. What do we need to multiply equation 1 by to get rid of the 2x in equation 3? -2. Good. Again, that does not change equation 1. We already rigged it, so this is a 0. -3 times 2/5 is -6/5 plus 2. So add 10/5, we get plus 4. Whoops, we get a 4/5 y. -3 times 2/5 is -6/5 plus 5/5 gives us a -1/5 z. The last one, -3 times 195 is what? 585. All right. So -585 plus 715 gives us what? 130. That's what calculators are for, right? I do promise that on your exam, the numbers won't be nasty. The process is the important part, not the numbers being gross. Okay. If you start getting gross numbers, you've made an arithmetic error somewhere along the way. Can't make the same promises for the homework, but I can for the test. Okay. All right, the next one, we want to multiply everything by -2 and add down. Again, it gets rid of this. We already rigged it so it gets rid of the 2x. -2 times 4/5 is -4/5 plus 5/5 gives us a 1/5 y. -2 times 2/5 is -4/5 plus 5/5 gives us a positive 1/5 z, right? -2 times 195, that's -390, and then add down and we get what, 45? So, like I said, this is what calculators are for, right? If you need help with all your calculators, I'm guessing have a fraction button put in them somewhere. So if you don't know how to use it, come see me. I can show you how to use the fraction buttons. Happy to do that. All right, so far so good? Yeah. What's the next step? Yeah, well, before I do that, I want to do something else first. I got a 1 here, so I want to get I need a 1 here, right? Agreed? Okay. So what do I need to do to get a 1 here? Yeah, multiply by the reciprocal works. Like I said, there's other ways that you could do it. You could, for example, multiply the third equation by 5 and then swap them, right? I'm personally, my personal preference, as you've got the calculators, is to just brute force it. Do what you get a 1, get a 0, get a 1, get a zeros. Okay. So let's multiply by 5/4 equation 2 and replace equation 2. Multiply by 5/4, we get a -1/4 z. And multiply by 5/4. Whew, do I really want to do that in my head? Not particularly. You may have that decimal. The 1.3 times 5/4. Thanks. This is why I said I promise on the test you won't get nasty numbers. They'll be whole numbers. Like I said, if they're not whole numbers, something went wrong along the way. All right. We got a 1. What's the next step? Okay, get a 0 below it, right? Make that y go away in the third equation. What do you need to multiply the second equation by to make the y go away in the third equation? Yeah, but I gotta do the opposite of it, right? I gotta do -1/5 equation 2 plus equation 3 and replace equation 3. Again, that gets rid of the 1/5 y here, right? Multiply by the opposite of the coefficient and add. -1/5 times -1/4 is positive 1/20. 1/5 is the same thing as 4/20. 1/20 plus 4/20 is 5/20, which gives you a 1/4 on that one. And then divide that by 5. What do you get? 0.325? Did I do that right? I take 1.625 and divide it by 5. 0.325? Yeah, then it'd be and then add down, so you should get a 0.125 when you're done. Almost done getting it in triangular form. What do you need to do to get it in triangular form? Multiply by 4, right? I want to get a coefficient of 1 on my z. So we'll do 4 equation 3, replace equation 3. Oops. Again, that does not change the first equation. Does not change the second equation. I think you get 0.5 when you do that. It's a cheap soda, 50 cents. Wondering what year this problem was written in at this point. Okay. This is now triangular, right? I got a 1x in my first equation, a 1y in my second equation, a 1z in my third equation. This is now triangular, yes? Okay. So now we work backward with that back substitution. So, back substitution. For y, you would put 0.5 in for z, and then add it over. You get 175, I think. 0.5 times divided by 4 is 0.125, and add it over. You get 1.75. Is that what others got? So you have the calculators. I don't have a calculator on me today. Yay, good. All right, last one. X plus 2/5 times 1.75 plus 2/5 times 0.5 equals 1.95. Let's see. Making a value for x on that one. 1.05. Okay. So now you have the price for each, right? So your pizza costs how much? Yeah, $1.07, $1.05. Your salad costs $1.75, and the soda costs 50 cents. Good. Putting your answer in context there. I know that took a while, but does the process make sense what we're doing? Again, numbers are a little ugly. Does the process make sense? Did the letters matter as you were going through the process, or were you more focused on the numbers? The numbers, right? So that's what we're going to do in the next section here. We'll get started. Well, first, talk about ways to keep track of the numbers, and then we'll talk about doing the same process of keeping track of the numbers. So I'll post solutions to the problems we did not do on the handout, so you have them. So you can see them for practice. Sorry. All right, so then in the next section here, we'll just do a little bit today. We'll finish it up on Wednesday. We're going to talk about matrices and how they relate to systems of equations. So just to start filling parts of this out. What we refer to in math, when we have a rectangular array of numbers, we refer to that as a matrix. The plural of matrix is matrices. Do not say matrices, but matrix. Matrices hurts my ears. It's kind of like saying vertices. Oh, it hurts my ears. Vertex. Matrix. Okay, sorry. I'll get off my soapbox. A rectangular array of numbers. You can see one there at the bottom of the screen where I've got this rectangular array of numbers here, right? So this is an example of a matrix. Each number that's in the array we call an entry of the matrix. So this particular matrix that you can see at the bottom of the screen has 10 entries to it. And we actually refer to these pieces as rows and columns. So notice this particular matrix has 2 rows and 5 columns to it. When we talk about numbers of rows and columns, we refer to the dimensions of the matrix. So we talk about the dimension of the matrix. It tells you how many rows and how many columns you have. We write this as what looks like almost a multiplication problem. If you have m rows in your matrix and n columns, we write what looks like multiplication. We say it's an m by n matrix. So we read that little, what looks like a time sign. We read that as by. Okay, so the m by n matrix. Sometimes in a matrix, we want to refer to a specific entry in there. So we use a subscript notation to do that. So whatever we typically will use a capital letter to refer to a matrix. So then whatever the corresponding lowercase letter is, we'll use to denote each entry. When we want to denote each entry, we use 2 subscripts. We use an I and we use a J. This is the I refers to the row number. The J refers to the column number. So anytime you're talking about matrices in dimensions or entries, the first number always refers to the row and the second number always refers to the column. So looking at this first example here, what are the dimensions of A? What's the dimension of A in this case? Two by 5, good. There's 2 rows and there's 5 columns, so it's 2 by 5. Okay. If I asked you for, well, not 3. Let's do it this way. If I asked you for A sub 2, 1, what would you tell me? 1? Because again, the first number tells you the row to look in, the second number tells you the column to look in. So it says go down to row 2 and column 1, that's a 1, right? If I asked you for A sub 1, 4, you would tell me 2. Because again, this is row 1, column 4. So I'm looking at that entry right there. Does that make sense? Okay. If you said something, if I did write something like I started to, what would you tell me that one? Where does that say to look? The third row in the first column, right? Is there a third row here? No. So this is just, there isn't one. Okay. The matrix only has 2 rows, so A3, 1 would be undefined here. Does that make sense? Now, every matrix you have will have fewer than 10 rows and fewer than 10 columns. If for some reason you went bigger than 10, you would put a comma in between the 2 subscripts so you could tell how many digits you were looking at. Just real quick, looking at this last one, what is the dimensions? What's the dimension of B? 4 by 3. If I wanted B sub, say 3,3, what would you tell me? Good. Yep, you're right. -8. Good. Third row, third column is -8. Yep. If I wanted B sub 4,2, you would tell me 4. Because I'm looking right here, right? Fourth row, second column. Okay. So this is just real quick introduction to matrices. Basically how we write them, how we refer to their entries. We're going to use matrices to help us keep track of a linear system and then do that same elimination process just by keeping track of the coefficients. So we'll talk about that on Wednesday. Again, I'll put answers up to the ones we did not do, the examples we did not do in the other handout, so you have those. I'll post those on Moodle for you. Otherwise, have a good one. We'll see you on Wednesday.